Here we will cover the secant line, the tangent line, and the normal line. We'll review or introduce what they are visually, and then we'll get into what information we need in order to write the equation for each of these lines if asked. And at the end, once we determine what we need to write, we'll verify that that is in fact all we need on Desmos. So we have three functions drawn here. We've introduced the secant line previously, but the secant line is a line that passes through two distinct points on a function. Okay, the term secant means to cut, so you can think of it as it cuts the function in two spots. Okay, so that would be an example of a secant line through 2 points. A tangent line is a line that touches the function in 1 point, so it's passing through only one distinct point. The normal line is related to the point of tangency for a tangent line. So we're going to redraw a tangent line. The normal line is the line that runs perpendicular to the tangent line at a point. So this purple line is what my normal line is. Okay. Now let's talk about what we need in order to write an equation for a line. So let's just do a quick concept review from back in the day when we studied linear functions. To write any linear function, so to write a linear function, you need two things. One, you need a point it passes through. And two, you need the slope or its rate of change. So that is all we need, in the format we're going to use is going to be our point slope form. Because if all we need is a point and a slope, that is the most efficient way to write the equation of a line. So a review of what point slope form is. Where y1 and x1, that's talking about the point it passes through. And as you're aware, m represents the slope or the rate of change. Okay, now let's look at the secant first. So for secant line, here's what we need. One, point it passes through. And you can choose between either point. Either point x1, f of x1, or x2, f of x2. Okay, it doesn't matter which one you choose. Something to keep in mind when we describe the points it's passing through. It's not unusual for you. You may be required to find the output value at that x value that's given. So may be required to find the y-coordinate. Again, to find the y-coordinate, you just take the given x value and plug it into the given function, right? So you may be required to do that. It's not always going to be given to you. And that goes for all three of these cases. Once we determine a point it passes through, we have our choice. The slope will be determined through average rate of change. And again, how do we determine average rate of change? I'm going to do f of x2 minus f of x1 over x2 minus x1, right? The change in the y values over the change in the x values of the 2 points that we're given. So that's how you do a secant line. Now let's do the tangent line. To write an equation for the tangent line, you take the point it passes through, we'll call it a f of a. Again, you may be required to find out what f of a is, and you just do that through evaluating the function f at a. However, we don't have a choice here, so we only have one choice. Because a point of tangency, or a tangent line, passes through only one point, so there's no wiggle room for that. Now, the slope for a tangent line is going to be the instantaneous rate of change at that point. At x equals a, or the other interpretation, the derivative. We said the derivative is synonymous with instantaneous rate of change, and it's also synonymous with the slope of a tangent line at a point, so the derivative at x equals a. So notationally, you may see something like we're looking for f prime of a, okay? So formatting, the standard format will equal y minus whatever the f of a is, equals f prime of a, because that's our slope, times x minus a. Okay, that's our general form for our tangent. And then lastly, what about our normal line? So for the normal line, again, we determine a point it passes through. So the point of tangency is the point it passes through. Again, that will come in the form, or some form, a, f of a. Again, repeating myself, but you may be required to find what f of a is. And then for the slope, because it runs perpendicular to the tangent, if the tangent is the instantaneous rate of change, to find a perpendicular slope, you're going to take the negative reciprocal of that. So we take the negative reciprocal of the instantaneous rate of change at x equals a. So we already said that instantaneous rate of change is the derivative. So this is going to be 1 over, or let's say, let's write this a little differently. Let's say if the derivative is equal to f prime of a, which equals the slope of the tangent at x equals a, then the slope of the normal will be the negative reciprocal of that. Okay, so flip it, make it negative, and there's the slope of the normal line. So our general format y minus f of a equals -1 over f prime of a, x minus a, if it's passing through the point a, f of a. So now, to verify that that is in fact all we need, let's hop over to Desmos and run through the visual and how to write these lines. So we have our function here. Let's say we want to write the secant line that passes through a point. So let's add some points here. A, f of a. And we'll add another point, b, f of b. We'll make them both sliders. Let's fix. So we'll move this point over here. Now, if we're going to write the equation, we can choose either of those 2 points, it doesn't matter, but we also have to calculate the average rate of change. So let's call the average rate of change m, and we will say the average rate of change is calculated by finding the change in the output over the change in the input between those 2 points that we're looking at. So we have a calculation. So now if I want to write the equation of my line, when we write this equation, we should see a line that passes through those 2 points. So let's choose, it doesn't matter which point, how about we choose a, f of a as the point it passes through. So we're going to do y minus the y coordinate, which is f of a, equals the slope, which we called m, the average rate of change, and then x minus a. And you can see that the line that pops up does in fact pass through those 2 points. And if we didn't want to define m previously, we could have just said that the slope, we could have actually typed in our average rate of change formula, and that should work just as well. Okay, so we could have done this, and we still get the same result. So we choose one of the 2 points, and I can change the 2 points. I can change this to f of b, and that should not change the line, and x minus b, to illustrate that either point is useful. And there you go. So there's our equation. We know we got it correct because it passed through our 2 defined points. Now let's say that we want a tangent line. So I'm just going to hide this for now. Let's say we wanted the tangent line at a, f of a. So the tangent line, we're going to do y minus the y value of the point of tangency that we want to pass through, equals the derivative at that point, which is synonymous with the instantaneous rate of change, which is what is needed for the slope of the tangent line. So we're going to write f prime of a, and it's going to pass through x minus a. And there you go. You can see that a tangent line has now been drawn at that point. And I use that derivative notation f prime, and make sure it's not f prime of x, but rather we want to evaluate the derivative at the point of tangency so we can get the slope at that specific point. Now, let's say we wanted to write the normal line. So I'm actually going to leave the tangent line so we can see the perpendicular nature of the normal line. We're going to do y minus f of a, because it's passing through the same point, but this time we want the negative reciprocal of our instantaneous rate of change. So we're going to do negative, and we're going to take the reciprocal, which is 1 divided by f prime of a, x minus a. And here we can see that this orange line that has now been added does in fact run perpendicular to our blue tangent line. And if we want to check to see if 2 lines are perpendicular, if we take the product of their slopes, we should get -1. So if I take, and I mean, you can see that here, where if we take f prime of a and multiply it by -1 over f prime of a, you'll get -1. But when we start to deal with actual numbers, when we calculate these instantaneous rates of change, a good way to verify that you have the correct perpendicular slope is to multiply the two numbers and get -1. So you can see from these images that what we decided is what you need is in fact all that you need. So you need a point that it passes through. You need specific slope calculations for specific lines. As a recap, secant requires average rate of change. Tangent requires the instantaneous rate of change, which is the derivative at the point of tangency. And the normal line requires the negative reciprocal of the instantaneous rate of change at the point of tangency. And that is a conclusion to secant, tangent, and normal lines.